Okay, welcome students to 1.1 differential equations. We're going to start off, once again, this is Professor Holtman, and welcome to differential equations in linear algebra. Okay, we'll start off with a short section, 1.1, and then we'll move into the next section. Okay, let me share my screen real quick. Okay, hopefully my screen is up now. Looks good. Okay, 1.1. Okay, 1.1. Okay, differential equations are everywhere. Okay, differential equations are everywhere. Okay, what is a differential equation? A differential equation, okay, is any equation that involves one or more derivatives okay, of an unknown function. Okay. We have two different types of differential equations. They're called ordinary differential equations. Okay, and these are of a single variable. Okay, so think of like a variable x. Okay, those are a single variable. And then we have something called partial differential equations. And those are multivariable, multiple variables. Okay, this course will focus on ordinary differential equations, or what we call ODEs. Okay, this is PDE is something that we save for later for people that want to do mathematics, study higher level mathematics, or it plays into engineering as well. And so you may take this as an undergraduate, but it's an upper division course. Okay, some people don't even take partial differential equations until they're in graduate school. Depends on the coursework that they're doing. Okay, partial differential equations are a little bit more complex. Ordinary differential equations not as complex. Okay. Let's look at some models where we see differential equations. Okay, we have a population model. Okay, and population models, differential equations come up. Okay, for example, we have dp dt is equal to kp. Okay, and this is our exponential growth model. Okay, the rate of growth is proportional to the size of the population. At any given time. Okay, so at any given time, the population size will dictate how fast the thing is growing. Okay, and this is, again, we can show that this is an exponential model, what we call an exponential growth model. Okay, we could turn this equation into this equation, P is equal to P naught e to the KT, okay, by solving this differential equation. This is the differential equation, or what we'll refer to as a DE. Okay, whenever you see DE in this course, it's going to mean differential equation. Okay, I just don't want to write out differential equation over and over again. It may be capital DE or lowercase de. Whoops, sorry about that. Okay, capital DE or lowercase de, but it's just going to mean differential equation. Okay. So maybe I'll write it out once. Okay, I won't write it out again. Okay, that's what that means, differential equation. Okay, so this exponential growth model, probably you've seen in other courses. Okay, that has a differential equation that looks like this. Okay, population growth model. Okay, another place that that differential equations come into account is something simple differential equation, Newton's law of cooling. And again, you may have heard about these things from other courses, either physics or math courses, and they just kind of give you the formulas. But now we're going to say, well, where do these formulas come from? And it's really based on a rate of change, okay, a rate of change over time. You know, it's like, well, why is calculus important? Because it's a rate of change. Okay, things that are changing over time. Okay, and then we can derive our models based on, you know, these rates of change. Okay, Newton's law of cooling. Let T of T, or the temperature at time T, denote the temperature of an object at time T. Okay, and let Tm of T, okay, T sub m of T, denote the environmental temperature. Note the environmental temperature. Sometimes it's called the ambient temperature, or you know, the room temperature. Okay, but sometimes room temperature is not the temperature that's ambient. Maybe you're in an oven, and that temperature is 400 degrees Fahrenheit, and that's the outside temperature, the ambient temperature, the environmental temperature. Okay. Newton's law of cooling. And heating. We could also say heating. Depends on if the temperature goes up or down. Okay, Newton's law of cooling, heating, is dt, the temperature as a function of time, change in temperature as a function of time, equals negative K, okay, of the temperature at time T minus the environmental temperature. Okay, so this is a rate of change, but it depends on the temperature you start with, and it depends on the temperature that is in the environment. So the case that makes most sense to me is basically like taking a cake out of the oven, right? That cake is going to be 400 degrees Fahrenheit when it comes out of the oven, or 350 or whatever you set your oven to, and then when it comes to ambient temperature or environmental temperature of 72 degrees in your house, there's going to be a rate of cooling. Okay, eventually, if you leave the cake out long enough, it's going to cool to room temperature. But you know, how do you model this over time, right? It's going to start it's going to start at a certain temperature. The other case can be made for, well, what happens if we take an ice cube out of the freezer? And that freezer is going to be maybe somewhere around, 0 degrees Celsius, or not 0 degrees Celsius, 0 degrees Fahrenheit, or like maybe 4 degrees Fahrenheit, or whatever your freezer is set to. Okay, and then it's obviously going to be below freezing. And then when you take that item out, or maybe it's a frozen dinner or something, that frozen dinner is going to heat up to the environmental temperature, to 72 degrees. And then once again, if you leave it out long enough, then it's going to reach room temperature. Okay, and so there's a rate of change there that's happening over time. Okay, and this differential equation models that rate of change. Okay. Okay, the negative in front of the K ensures that K will always be positive. Let's explore that for a second. The negative in front of the K will always ensure that the rate of change, okay, is that the constant here is always positive. Let's write that down. The negative sign in front of the K will always ensure that K will always be positive. Always ensure that K is positive, a positive value. Okay, and why is that? Okay, well, let's look at the two cases. Case one is when we have Newton's law of cooling. Okay, case one is when the temperature of the item is greater than the ambient temperature, or environmental temperature. Okay, when T is greater than Tm, then, and we let K be positive value, then that tells me that the rate of change is negative. It's going down. Okay, then the object is cooling. Okay, and dt dt is less than 0. Okay, so the rate of change is negative. Looking at a picture, we could see that if we said that the environmental temperature was my baseline, if I start, okay, at T naught, or T sub 0, or we would call that T at time 0, this would be the time when you take the cake out of the oven. It would start here, and then it would go down until it eventually became room temperature. Okay, so what does that mean? That means that dt, d capital T, d lowercase t, capital T, again, is temperature. Lowercase t is time. So this is a change in temperature over change in time. Change in temperature over change in time. And we can see that the slope of the tangent line here would be negative. Okay, no matter where you're at, the slope is negative. Okay, because it's cooling, it's going downhill. We've got a downhill trajectory. Okay, we've got a decreasing function. Okay. That's case one. Okay, case two, okay, is T is less than Tm. Okay, so if T is less than Tm, okay, then T minus Tm, if this is a smaller number, then this is negative, equals a negative. value. Okay, then we can say let's use some better algebra here. This is less than 0. Okay, so yeah, you could just toss the tm to the other side of the inequality, and we would get t minus tm is less than 0. Okay, so this is a negative value. So what happens when we do a negative k times a negative value? We get a positive k. Okay, and that would mean that dt is positive. It's greater than 0. Okay, which means that we're going uphill. We're increasing, which should make sense because if the temperature of the item is less than the ambient temperature, then that's going to increase. It's going to increase and approach the environmental temperature. Okay. And we can see that the slope of the tangent line here, again, is getting kind of messy. Let's clean that up a little bit. Okay, the slope of the tangent line, make this a little nicer, sorry. Here we go. Okay, the slope of the tangent line is a positive value. Man, messy. Is a positive value. Let's just do a tangent line there. Slope of the tangent line is a positive value. Okay, and has a positive slope. So dt is greater than 0. Okay, it can be shown, and we'll do this later when we're solving some of these differential equations. It can be shown that the temperature at time t is equal to the ambient temperature, environmental temperature, plus some constant, some cooling coefficient, e to the negative kt. K is the rate of change. Okay, it's the growth or decay rate based on how fast this thing is changing. Okay, we can solve this differential equation into this equation there. It all stems from the fact that we know something about the behavior of the change in this model, in this system, in this closed system. Okay, one other thing that we see that we can use some of these differential equations for, there's a lot of applications. These are only 3 specific ones. Okay, orthogonal trajectories. Okay, so orthogonal meaning perpendicular. Okay, orthogonal trajectories. Okay, the family of curves. F of, let's make that capital F. Capital F of X, Y, and C. Okay. C is a constant. Okay, the family of curves F of X, Y, and C, and G of X, Y, and K. Again, K is another constant. Okay. Have orthogonal trajectories. Have orthogonal trajectories. If, okay, it's not guaranteed that they have them, but they do if at any point of intersection, at any point of intersection, their tangents are orthogonal. Orthogonal. No. Okay, orthogonal. Okay, if the derivative of f is y prime, then the derivative of g is -1 over y prime. Okay, that's if they're orthogonal. Okay, let's see how this works in practice. Okay, example 1. Find the orthogonal trajectories of the family of curves. Find the orthogonal trajectories of the family of curves y squared equals cx. Okay, y squared equals cx. So we want to find the orthogonal trajectories of the family of curves. Okay, these curves, what do these curves look like? Okay, well, these are basically, if I could solve this for x, I could get x is equal to 1 over c y squared. And this is a family of parabolas. Okay, parabolas that go through the origin and are oriented along the x-axis. So, and that c will dictate whether it's wide or narrow. So we would get, if c was 1, we would get our kind of normal parabola. I'm not too great at drawing parabolas, but you get the idea. If c is 1, if c is greater than 1, we get, if c is greater than 1, we get a skinnier parabola. If c is -1, we get this guy flipped. And if c is negative is smaller than -1, I get this. What if c is between 0 and 1? I get a fraction, but when I do 1 over a fraction, it makes it a larger value, and so I would get a wider parabola. And so we get, you know, this is a family of curves. We get all of these parabola, and it's a family of parabolas. Okay, I probably should have used different colors, but you know, you get the idea here. Okay, it's a family of parabolas because we can let c be whatever we want. Okay, but you know, by letting x, y, and c vary, we can lock in a c, and that will create a certain parabola, and then it just gives us a family of parabolas. Not everything is going to fit into this definition, but we have that constant there that can vary. It is a variable, but it kind of locks in place which parabola we're looking at. Okay, it's just a third variable that gives us this family of curves. And so they're saying, look, we want to know what is orthogonal or perpendicular to these family of curves. Are there any other curves? Is there a family of curves out there that are always perpendicular to these? And so what we can do is we can solve the differential equation here based on this guy. So if we take the derivative, okay, of this with respect to x, okay, let's see what we get here. Okay, so d dx with respect to x, okay, is equal to 1 over c, or sorry, d dx of 1 over c y squared. Okay. Okay, so we're going to kind of implicitly differentiate this thing. The derivative with respect to x of x is 1. The derivative with respect to x of 1 over c y squared, that's going to be, well, y is a function of x. We're going to treat y as a function of x. So this is going to be 1 over c times the derivative of y squared, which is 2y, times, this is a chain rule, times a dy dx. Okay. Okay, so I'm going to multiply, I'm going to kind of solve for dy dx here. So let's multiply both sides by c and divide by 2y. And I get dy dx is equal to, okay, c over 2y. Okay, now, okay, is there a way to simplify that so that it doesn't involve c? Well, yeah, there is actually. I just want something that involves just x's and y's, if at all possible. I don't want to have that c because the family of curves that are orthogonal, they don't have c in them. It doesn't have a c. It's in some sort of other constant here, k. So I want to get rid of that c. I just want to focus on one curve, the derivative of all of these curves should have one specific derivative. Okay, one function for the derivative based on where you are at, x and y. Okay, and so we're going to solve the original equation that we've been given. I'm going to solve this for c and then plug it in so that we get just x and y. If I multiply both sides of this equation, x equals 1 over cy squared by c, okay, we get y squared is equal to cx, and then we divide by x. We can see that c is equal to y squared over x. Okay, c is a function of x and y there. So what am I going to do? I'm going to substitute that into my equation for the derivative, and I get dy dx is equal to y squared over x all over 2y. That will simplify to dy dx of y squared over 2xy, and one of these y's will cancel, leaving me with just y over 2x. Okay, so that's the derivative function for my original parabolas. Okay, for that family of curves, you give me a x and y, and I'll tell you that at that point x and y, I'll tell you what the slope of the tangent line is. Okay, it doesn't matter where you're at, okay? For any point, there's a specific parabola that's going to go through that point, and you give me that xy value, I will tell you exactly what the slope of the tangent line to that family of curves of parabolas is. Okay, very powerful. Okay, so dy dx is equal to y over 2x. Well, what about the orthogonal trajectories here? What would be orthogonal, or basically to right angles? Are there any functions that are going to be right angles to all of these values? Is there a family of curves that are always perpendicular to this family of curves? Well, if that is, then if I took this as the tangent line of that, then the derivative of the family of curves that I'm looking for, that would be here. here, right? The family of curves, so they're always negative reciprocals. The slopes, right? The slopes of perpendicular lines are always negative reciprocals. So I'll call this y prime of my original or y prime of, I'll just do the O for original here. Okay, maybe I'll just do y prime g or OG. Okay, original. Okay, so the y prime original is equal to y over 2x. So y prime orthogonal, okay, maybe we'll let the derivative of the r, rise of r, orthogonal. Okay, this is going to be my orthogonal derivative. Okay, those orthogonal derivatives are going to be the negative reciprocal. It's going to be negative 1 over y over 2x, which becomes negative 2x over y. Okay, so that's the derivative of the orthogonal trajectories. So what would be the family of curves, the functions that produce this derivative, this negative 2x over y? Well, if we go dy dx of the orthogonal trajectories is equal to negative 2x over y. Okay, and we were to kind of separate out the variables here. Let's cross multiply. Okay, multiply y dy is equal to negative 2x dx. Okay, so we're going to cross multiply. And we can now take the integral of both sides. We can say, oh, well, what's the integral of y with respect to dx, dy, sorry, with respect to dy. Now we're not integrating with respect to dx. Okay, this is y with respect to dy. Well, that's real easy. That's y squared over 2 plus constant. I'll let that be a c1, constant 1. Okay, and then what about over here? Now it's negative 2x integrate that with respect to dx. That's going to be negative 2x squared over 2. The 2's cancel, and I'll call that plus c2. Okay, so we integrated both sides. So we get x squared over 2, okay, is equal to, or plus c1 is equal to negative x squared plus c2. Now this is a y. Now let's clean that up a little bit. Okay, well that's we got rid of the 2, right? On that side, yeah. Okay, so now let's clean that up a little bit. Okay, so let's toss the x squared to the other side. Okay, and we get x squared plus 1/2 y squared. Okay, let's subtract off the c1 from the c2. Now, if I subtract a constant from a constant, don't I just get another constant? Okay, and I'm just going to call that constant c. Okay, that's just let's call it k. Okay, constant k. Okay, because that's really what we want. We want some function g, okay, in terms of x, y, and k. Okay. Okay, so some function of g in terms of x, y, and k. And so this x squared plus 1/2 y squared is equal to k. Okay, if I were to divide both sides by k, I would get x squared over k plus y squared over 2k is equal to 1. And what do those look like? What form of the equation are conic sections does that look like? Okay. Yeah, to me it looks like ellipses. Okay, where k is a, the square root of a, sorry, a squared, and 2k is b squared. Okay, so a squared is k, and b squared is 2k. Okay, so we get what's called a family of ellipses. Ellipses. So they're saying that if I take some ellipses here, or ellipses is the correct plural pronunciation. If I take some ellipses, they're saying that I will get orthogonal trajectories. These will always be perpendicular no matter where I'm at on the family of ellipses. This is a family of ellipses. Okay, and those family of ellipses, they will always be perpendicular to the family of parabola. Okay, those family, now my drawing's not as good as one that can be computer generated. So let me show you on Desmos graphing software. Okay, so let's see if we could go to Desmos. Okay, where's my favorites? Okay, let's go to Desmos. Let's see what we can get from Desmos here. Okay, so Desmos, I'm going to type in, let's do our original one, which was our family of curves, y squared equals cx. Okay, y squared is equal to cx, okay? So let's do c and then x, okay? And it says add a slider c? Absolutely. Slider just lets me change the value of what c is, okay? So y is equal to cx. So if I change the value of c, you can see that it gives me a representation of all the values in that family of curves. Okay, now it's not going to show you a bunch of them unless I put in, you know, y squared equals 1, y squared equals 1x, y squared equals 2x, y squared equals 3x. Then I could, you know, if I plugged in, you know, oh, another one, y squared. Where's my, there we go. Y squared is equal to 3x. Then it'll give you, you know, you can represent all of them, you know, as many as you want on the screen, but I'm going to represent all of them by just having this slider. Whoops. Just having this slider that shows me, oh yeah, you know, if I want to get a representation of every single graph that's in that family, we have a representation of every single graph that's in the family. Now, what's interesting is when we go to the next one, which was our orthogonal trajectories, or the family that is always perpendicular to this family. And we can see, oh yeah, you know, if we let x squared plus, x squared over k, well, yeah, that's fine, x squared over k. There it is. Okay, add a slider, yes. X squared over k plus 0 over, okay, plus y squared, oops, y squared over 2k. Okay, and we're going to let that equal 1. Whoops. 0 over equal 1. Okay, now we can get, basically we can manipulate c and k, however we want, we can manipulate this so that no matter what they are, okay, they're always going to be perpendicular. Okay, they're always going to have perpendicular slopes, perpendicular tangent lines is what I should say. Okay, the slopes of the tangent lines are always going to be perpendicular, no matter where I'm at on any of these two. You know, on the ellipse, however big the ellipse gets, or however I manipulate the ellipse, or however I manipulate this guy, it's always going to be perpendicular. You can kind of see that as we go around. Okay, it's always going to be perpendicular, no matter where I'm at. That's kind of cool. It's a cool little thing about mathematics. Okay, I will see you in the next one. Yeah.